In the previous tutorial, we saw how the schema for one of our axioms, modus ponens, can be filled in by propositions of any degree of complexity. So a way to think about this is that the modus ponens schema is represented by these geometric shapes. And as long as the contents of those geometric shapes are well-formed formulas and also are consistent with respect to the shape, then we're satisfying the schema for modus ponens. So what does that actually mean in English? What it means is that whatever goes in this box has to be repeated exactly in this box, and whatever goes in this box has to be repeated exactly in this box, and whatever operators we may have here, like this material implication, it has to be present in the first the first premise of the schema. So that's what happened here in this formal proof. In this proof, we saw that the contents of the box could be P and Q. The contents of the triangle, R or S. Those two are connected by the material implication to form the first premise of modus ponens. The second premise is the square. The contents of the square are repeated exactly. P or Q is the antecedent, and it reappears again in the second premise. And that entitles us to draw the conclusion whatever the contents of the triangle are, in other words, the consequent of the material implication in the first premise of modus ponens. And in this case, it's R or S. So now, given the fact that our schemas can be populated, as it were, by propositions of any degree of complexity, plus the fact that we can apply axioms that we need as many times as we need them to make a proof work out, we can prove a huge variety of different arguments by that combination, right? So we're going to look at two rules or axioms. One we just looked at, modus ponens. Here is the schema for modus ponens. So that's modus ponens. And one I introduced in the introductory tutorial on proof theory. This is simplification. So if we have two well-formed formulas connected by an conjunction, we can conclude either the front end or the back end. This is called simplification. All right, so this is two axioms that we're going to use to make a formal proof of a slightly more complex argument. So here's our argument. P implies R and S. The second premise is P and Q, and the conclusion that we're aiming for is going to be S. Okay, so that's line 1, line 2. So those are the two premises that we're given. Again, it's P implies R and S, and the second premise is P and Q. So now I'm going to construct this proof and show you how we can apply multiple axioms in order to complete a proof. That's a little different than the thought process for working out how the proof is going to work. We're going to talk about that as we go through the inference rules, and we'll practice on that. But for the moment, I'm mainly interested in showing you how we can use multiple axioms in order to bring a proof to a successful conclusion. So I'll add a little bit of the thought process here. If you look at line 1, you will see that the major operator is material implication. So when you see that, you should think to yourself, maybe that's the first premise of a modus ponens. But I would need the second premise. And so if line 1 is the first premise, what would the second premise be? Well, if line 1 is the first premise of modus ponens, this would be its overall shape, right? In the square, we would have just the variable p, and in the triangle, we would have the well-formed formula r and s. So, in order for me to make modus ponens work, I would need p on a line by itself. Now, look at line 2. Line 2 has a major operator of conjunction, and whenever you see that, you might think to yourself, well, simplification is one of my options. And sure enough, simplification gives us the ability to take one side or the other of a conjunction and as our conclusion. So that's what we will be able to do here. If we conclude P from line 2, now this is line 3 obviously, and our justification is simplification on line 2. Notice that simplification in both of its forms has only one premise. So simplification has one premise and a conclusion, so that means we're going to only index one line number, and we're going to state what line we applied simplification to. So here's what we did. Looking at line 2, we looked at the right hand and the left hand side of the conjunction, and we concluded just the right hand part. Okay? Given our reason, simplification, what we applied it to, line 2, and so what we got on line 3 is P. But P is exactly what we need to make modus ponens work with line 1. So now look at line 1. On line 1 we have P implies R and S, and now we have the second premise of that modus ponens, so that enables us to conclude on line 4 everything in the triangle, which is R and S. So notice, that's everything that's in the triangle. So in this case, the triangle is the triangle of the modus ponens schema, right? So don't confuse all these shapes. Like the triangle on line 2 is the triangle for simplification. How do we know that? Because that's the major operator of simplification, and that's what we applied when we derived P. Okay, so what we've done is we've applied modus ponens to which lines now? The first premise of modus ponens appeared in line 1, and the second premise of the modus ponens appeared in line 3. So we write modus ponens 1 and 3, and that gives us the expression R and S. But notice, what we want to conclude is S. So when we look at line 4 and we see that the major operator is a conjunction, once again, it should spring to mind that simplification is one of our options among the axioms. And sure enough, there's a version of simplification that's perfectly suited to the purpose here. So if we take R as being the left-hand side of a conjunction and S as the right-hand side, and using the second version of simplification, the square and the triangle, and we conclude the triangle, then on line 5 we can conclude everything in the triangle, which turns out to be S. So again, now we're talking about a square and a triangle that are the schema of simplification, not the schema of the previous application. Remember, R and S was the triangle from modus ponens, right? But once we have that on a line by itself, R and S, then it becomes free game to do other things to it, like apply simplification. So that's what we did. We applied simplification. And to which line? We applied it to line 4. And now notice, the S that we have by itself on line 5 is exactly the S that we wanted to conclude in our original argument, and so the proof ends. Now, I'll just do one more thing, and that is I'm going to rewrite this whole proof without the geometric shapes so you can see a little more clearly what the proof structure looks like when it's not all annotated with those geometric shapes. So that's our actual argument setup, right? So on line 3, the proof begins. We conclude P by modus ponens on line 2. I'm sorry, by simplification. I was thinking it sets up our modus ponens, right? So on line 4, we conclude R and S. Now modus ponens on lines 1 and 3. And on line 5, we conclude S by simplification on line 4, and we write QED because the proof has ended. All right, so aside from my mistake calling line 3 modus ponens, you'll see that the rationalizations here, the justifications are all exactly the same. So the only thing that's missing in this version of the argument of the proof is the geometric shapes that were intended to help guide us in recognizing the schemas. So if you think about these geometric shapes as the overall shape of a schema, it may help you track how you're manipulating the bits and pieces as you construct the formal proof. But the geometric shapes are really an aid to a human being. They don't really have anything to do with the formal proof. This is what the formal proof actually looks like.